Good idea.
Okay, perfect.
Oh.
So it's going to be recorded and then you have to store in the cloud, and then I'll be able to download it after this whole thing is done. You know, it takes some hours for Zoom to process all those recording, and I'll share it with Rodrigo after probably tonight or tomorrow.
Okay. Yeah,
right.
maybe you can start right now. Yeah, you're going to
Still 1 minute.
I have about 43 participants already, and people is going to join in. But what about we start? Joe, are you happy to start right now?
Yeah, I mean, I'm always happy to go. I mean, it's up to you and Rodrigo to decide
Okay,
whether.
I'll just do a first announcement, then I ask Rodrigo to introduce you. Okay. All right. So just tell me when you are open to the audience.
I'm ready. Yes.
But the audience is already listening us.
Yeah, I think so.
Okay. All right. Okay. Hello, everybody. It's a pleasure for me to host this talk by Professor Cho from University of New York, and he's going to talk a bit of his work. It's been done in natural language processing, and it's a pleasure for us in this class that we have also Rodrigo, his former student, helping us in this course. And it is very, very, I'm sure this talk will be very instigating for people in this field, which is a new field for mainly most of our audience are not people that are very familiar with natural language processing, but most of them are very familiar with deep learning. So I'm very curious and very looking forward to hear for your talk. I'd like to ask Rodrigo to introduce Professor Cho, and thank you again.
All right. So yeah, welcome everyone, and thank you all for coming. Yeah, I'll just say a few words about myself. My name is Rodrigo Nogueira, and I did my undergrad and master's at UNICAMP a few years ago. And I recently got my PhD from New York University. I'm moving back to Brazil in the upcoming weeks. So in case you want to reach out, yeah, I'll be very close. And yeah, today's talk is part of our deep learning for natural language processing class at UNICAMP. It was taught by me and Professor Roberto Lotufo, and who was my master's advisor. And yeah, we've seen this explosive growth in the field of natural language processing the past few years. Thanks mainly to recent advances in machine learning, especially deep learning. And then we decided to make this talk public so more people can learn about this fascinating area. And we also want to foster the growth of the community in Brazil. And I think for this, nothing better than hearing from one of the world leader experts in the field. So yeah, it's my pleasure to introduce you to Professor Kyunghyun Cho. Professor Cho is an associate professor of computer science at New York University. And he is well known for his contributions to neuromachine translation, natural language processing in general, and especially the development of the attention mechanism, which is today used by all the best performing systems for machine translation, web search, question answering, chatbots, and so on. Yeah, Cho, as Professor Roberto mentioned, he was my PhD advisor. He's a great person to talk to, and I hope you enjoy the talk and stay long for ask questions. Yeah. And well, without further ado, I'll pass the mic to Professor Cho, and thank you.
All right, thanks for the generous introduction, and then thanks for the invitation in general. You know, I haven't actually been to Brazil, and then it would have been awesome if I could go there, you know, in person. But you know, once the pandemic is over, and then when the world comes back to the normal stage, you know, I'll try to stop by and say hi in person and so forth. So you know, I was invited, and I decided that okay, I had to decide what I was going to talk about. And I heard that this is a course on deep learning for natural language processing. So I thought, okay, so then I'm going to give some background about how I have been introduced to deep learning for natural language processing, and then what I have seen over the past 5 years. And the 5 years is the time during which the whole, let's say, this subfield of natural language processing using deep learning has just, you know, exploded. And then I thought it's going to be a good kind of chance for me to share what I have seen, and then how much actually how much state of the art I have not been able to achieve. That's why the title is going to be the state of the art list and novelty-less journey into neural sequence model. So it turned out that the deep learning for natural language processing is not a new thing at all. In fact, this whole thing started 30 years ago when Bob Allen in 1987 wrote a paper in which he described a translation as a way to map from one language to another and then using backpropagation algorithm to figure out what that mapping is. And that was followed shortly after in 1991 by Lonnie Chrisman, who was back then at CMU, who again thought of machine translation or the translation as trying to map a distributed representation of source language into distributed representation of target language. Now, of course, none of these actually worked out. Their experiments were too small a scale. Their computing resources were, of course, cannot even be compared to the kind of resource that we have these days. In 1997, two groups in Spain, led by Forcada and Castaño, proposed the same idea. That is, let's try to use a neural network or deep neural networks to learn this mapping from one language to another to build a machine translation system without having to design all those complicated rules in how to perform or conduct translation. So in other words, what I'm going to tell you today about my 5 to 7 years, the past 5 to 7 years of journey, there's nothing really new about it. We already knew in 80s and early 90s that this kind of deep neural network that we use these days had to be good for natural language processing and in particular machine translation. So in my particular case, my own journey in natural language processing or deep learning for machine translation started in 2013 when I arrived in Montreal at Yashua Benjo's lab as a postdoc. So when I arrived there, Yashua told me, okay, there are 4 things that he had in his mind that I could work on and that I could choose to any one of them. First one was to continue working on restricted Boltzmann machines, which is a type of the generative neural networks that nobody really cares anymore, but I wrote my dissertation on. And second was something called generative stochastic network, which was supposed to be one of the greatest generative neural network of all time. Haven't you heard about it? Yeah, me neither. I haven't heard about it for the past, let's say, 5, 6 years, because it didn't really pan out well. Although the ideas from generative stochastic networks that is based on denoising autoencoder still lives on, and then I myself actually use it for my own research, and I'm going to talk about it almost at the end of this talk. And then the third option was machine translation. Fourth one, I don't even remember. When I heard machine translation, I got stunned. I mean, I have no idea about machine translation, not to mention natural language processing. And I asked back to Yashua, I don't think anybody at the lab knows enough about machine translation and natural language processing. However, it just sounded so intriguing. That's why I decided to work on machine translation. In 2013, when I joined Montreal, and then once I decided to work on machine translation, I was given a chance to give a talk at a kind of weekly lab meeting because the Mila was so much smaller back then. And then in that lab meeting, I decided to talk about some of the vision I had about how to build a machine translation system out of the deep neural networks. And then this slide, which I just copied and pasted over from my talk in 2013, had in fact a very nice idea, is that we want to build an encoder that's going to read the source sentence one word at a time, and then figure out the distributed representation of the source sentence. And then given the distributed representation, we're going to build a decoder neural network that's going to generate one target word at a time until it generates a full sentence. And it turned out that this idea actually worked. Well, it worked, but a bit with a disappointment. We built this neural translation system using LSTM or the gated recurrent units that we kind of invented ourselves back then. And then we built this standalone neural net, purely neural net based machine translation system, and it did not work as well as the phrase-based translation system that was the de facto standard back then in machine translation. And this was in fact the observation that was already made a year before at EMLP 2013 by Phil Blunsom and Noel Cockbrenner, both of which are at Google and DeepMind. And then what happened is that when we built this system, the system's BLEU score, you may have learned about BLEU score already from Rodrigo, was so low that we couldn't really use it for anything reasonable. Only thing that we could tell about the usefulness or the potential of such approach was when we combined this with the existing phrase-based system that is Moses plus RNN encoder, or the Moses plus LSTM on this slide, we could see that this approach could improve the existing system. But of course, we were still far and far away from the state of the art on any of the data sets that we have tried our system back then. But thanks to one of the reviewers who saw the potential of this approach, we were able to publish this, and then this kind of started the whole stream of interest in neural net for machine translation. And then the one thing we knew already back then was that it had to work. And then we knew that already in 80s and 90s, it had to work because these neural nets are very powerful and can learn any kind of nonlinear transformation of the input into the target. And the machine translation is really nothing but transforming a source sentence into a target sentence, right? And what we saw was that at the end of 2014 at NeurIPS, Ilya Sutskever, who is now a research director at OpenAI, presented a surprising result where he showed that when he scaled up this very simple neural net-based machine translation system without any attention or anything, and then ensembled 5 such systems, they were able to, in fact, go beyond the existing phrase-based system that was not really well-tuned, but that was still the amazing thing. And then it was a pretty interesting to hear Ilya's conclusion back then, is that if we can solve this problem of machine translation using this gigantic neural network, then that actually implies not only that we can solve a machine translation, but also solve a generic algorithm. Because what are the computer algorithms? Algorithms are a machine that takes as input a sequence and then outputs a resulting sequence. Right? So that was an interesting conclusion Ilya made. However, it really wasn't working for me and my team in Montreal. What was wrong there? Because Ilya back then, well, to start with, Ilya is so much better software engineer than I am. So he was able to actually code up the entire thing to work with the 8 to 16 GPUs in parallel, coding everything from scratch. Not like us, we are now using PyTorch or TensorFlow is so much easier. But back then, Ilya was coding everything in C++. And I just didn't have a engineering skill to do so. So we had to look back into the model and then the learning algorithm that we were using, and then trying to figure out what are these roadblocks that prevented us from getting the good enough results when we know fundamentally that these approaches had to work. And one thing that we noticed was that our approach that was using a neural network that had the encoder and decoder was in fact able to translate sentences that are short very, very well. In fact, almost as well as the existing phrase-based systems, except that the performance or the quality of translation degraded extremely fast as the length of the source sentence grew. And then what that implied was that our network was just not large enough in order to be able to compress the source sentence that contains a lot of information into a single vector, continuous vector, and then be able to decompress it into another language. So in other words, we identified compression as an issue. And then once you identify a problem, then there's time for you to actually come up with a solution. Now, I'm just saying this because whenever I talk to my PhD students or the master students who are especially in the junior years, they often come up with a solution first and then try to find the problem or the, let's say, issue the solution is going to solve. But often the other way around is so much easier. So identify the problem and then try to come up with a solution. So we identified the compression as a problem. And then people in Montreal back then, we were just spending the whole summer trying to come up with a solution that's going to avoid this issue of compression. I came up with a computationally horrible idea that is, every time we generate one target word, let's try to reread the entire source sentence and then try to figure out what the next word should be. This is computationally horrible because what it means is that the computation complexity is going to be quadratic with respect to the length of the source, assuming that the target length is similar to source length, which is almost always true in the case of machine translation. But it's too expensive. It doesn't make any sense. Back then, Dima Badenow was a master's intern in Montreal working with me. And then he came up with this amazing idea. And then that idea is the attention. Instead of trying to reread the whole thing, we're going to compute the representation of the source sentence first, but it's not going to be a representation that's going to be a single vector, but it's going to be a set of vectors where the cardinality or the size of the set changes with respect to the length. So if there are a lot of things to capture, there are going to be many vector representations of the source sentence. If there are only a few things to capture, then the number of vectors is going to be small. And then what we're going to do is every time we generate a new word, we're going to look back into this set of representations, weight each one of them according to how useful each one of them is going to be for predicting the next word, and then compute the weight itself. It's a beautiful idea, right? So it's pretty rare to have this kind of moment, but at that moment when Dima explained his idea to me, it was so clear that it was going to work because we knew what the problem was, and then the solution elegantly addressed that problem directly. So we completely avoided the issue of compression. And then it helped tremendously to build a system that is going to work better and then that is not going to degrade as the length of the source sentence decreases. But the interesting thing is that even then, with our resources and with our engineering skills, we couldn't really get to the state-of-the-art performance. So, I don't know if you're on Twitter or, at the other social media, you notice a lot of people complaining about reviewers are just shooting down all these papers just because there's no state-of-the-art results, or, a complaint saying that, the people only chase the state-of-the-art result. But, clearly, state-of-the-art is just a one thing that lets us validate the idea. But when you know what the problem is, and then that the solution is designed to address this problem, you don't actually need a state-of-the-art, right? The nice thing is that this attention mechanism actually gives us a way to visualize what goes on inside. And then what we saw when we did this kind of visualization for the first time that you see on the right side of the site, we immediately knew that this attention mechanism was solving the problem of compression that we identified. I think that that's the reason why this paper was accepted at iClear 2015 and then was presented as an oral presentation. Now, back then, as I said, no one at the lab in Montreal knew that much about machine translation, nor natural language processing to start with. And then that included myself. During my PhD, I worked entirely on generative neural network, in particular restricted Boltzmann machines, and did nothing that has anything to do with natural language. So only thing that we did was to stick to the English-French translation using the data set and the evaluation protocols provided by our collaborator back then from the University of Le Mans in France. So once we came up with this attention and then saw that this actually has solved the problem that we couldn't solve, that is the problem of compression, we got curious. Does this new technology generalize to a language pair beyond English and French? Because English-French is they're pretty similar languages to each other. Also, can this new technology be competitive against the state-of-the-art back then, that is the phrase-based machine translation system? And of course, machine translation has a very long history going all the way back to 1940s. And then there is a very solid way to evaluate how the new systems work against all the other existing systems. And then one of them was to participate in the machine translation competition or the shared task at the WMT, which is short for Workshop in Machine Translation, or now it's been renamed to Conference of Machine Translation. So Orhan Firat and Sebastian Zhang, Orhan, who is now at the Google Translate, and Sebastian Zhang, who is my PhD student. So we were sitting in Mila in Montreal, and the three of us spent, just a couple of nights trying to build this first participating neural machine translation system for the WMT in 2015. And then to do so, we had to actually come up with a lot of new ideas, one of which was to try to build a machine translation system, or in fact, any kind of neural network system that's going to be scalable in terms of the number of outputs. So when you build a neural network classifier, you often build a classifier that's going to work with 100 classes, 1,000 classes. But in this kind of language processing, as you have learned this semester, you need to work with the tens, if not hundreds of thousands of classes. And then nowadays we have a gigantic GPU memory, and then we have a very fast processors and so on. So it's less of a issue, but back then it was a bit of an issue, right? 2014 and 15. So we came up with the idea to use the importance sampling, and in order to scale it up. Unfortunately, the paper was rejected, but when we participate in WMT for English to Czech translation, English German, Czech to English, German to English, and Finnish to English, our systems in fact were one of the top ranked systems. And it turned out that the human evaluation also showed that in terms of English-German translation, this purely neural machine translation system, which was the first time that the neural net alone system participating in WMT was indeed as good as the state-of-art system that relied on the syntax and phrase-based neural machine translation system. Although unfortunately for other languages, we're only, let's say, the third and fourth, but it was a great indication that this new paradigm can be the paradigm for machine translation. And now, last year when I checked for WMT 19, all the leading systems that have participated in this shared task of the news translation and any other translation are neural net-based systems. Of course, none of them are from my own lab because I haven't really pushed it forward on trying to get the state-of-the-art system, but it's pretty nice feeling to see that what I kind of contributed as a at the beginning of this paradigm, and then this paradigm has now become the standard in machine translation. But of course, this was just one thing that we're looking at already in 2013. What we were more interested in back then was the power of this representation that is shared across multiple languages. The idea was that this whole process needs to work with the many, if not all the languages in the world. We want our representation to be agnostic to which source language we're talking about, and we wanted our decoder to be able to decode out the actual sentence into whatever the target language we want it to be from this shared representation. And then it turned out that I actually talked about this in 2013 in the TED-talk, and then I completely forgot about this while working on trying to get this neural net to work on this single language pair translation. And of course, there's nothing new under the sky, right? So already in 1991, Lonnie Christmas, a Christmas that we talked about at the very beginning of my talk, already talked about building such a multilingual neural machine translation system. In particular, he was looking at having two source languages, English and Spanish, and then two target languages, which are also English and Spanish. And of course, if this kind of multi-way, multilingual translation works, then there are so many advantages. And then two of which, if I were to take some examples, include high resource to low resource knowledge transfer. Because we have more than 7,000 languages in the world that are not dead, right? All of them are active. And the amount of resources that are available is very much skewed toward a top 10 to 30 languages. So it's necessary, and then it's actually very important for us to be able to transfer knowledge from those high resource languages to low resource languages. And then this multi-way, multilingual translation was supposed to do that. And second advantage was the number of parameters grows linearly with respect to number of languages, as opposed to the quadratic growth of the number of parameters when you build the machine translation system for every possible language pairs. And then you did this should only help. Those were the advantages. Obviously, there were so many challenges. One of them was that, okay, we didn't really have any multi-way parallel corpus other than the resources from EU Parliament. But EU Parliament proceedings are pretty small, so we cannot really just rely on this. So we had to come up with a way to use all possible unaligned collection of parallel data. And then we decided to look at the English, French, English, Czech, English, German, English, Russian, and English, Finnish, which are the languages for the shared task back then at WMT. And you see that even among these five language pairs, the difference in the amount of resources, in fact, is quite significant. The second challenge was that we just did not have enough compute resources or a nice framework to use in 2015. We are using Theano. I'm not sure if any of you have tried it. Theano is an amazing framework. I used it quite a lot. I contributed to the recurrent neural net part of Theano myself as well. However, it was not easy to scale it up to multiple GPUs, not to mention multiple CPUs as well. Of course, so the Orhan Firat, whose picture is shown here and who now works at Google Translate and Google Brain, had to hack Theano significantly in order to scale it up to work with up to 8 GPUs and working with all those 5 language pairs simultaneously. And then we actually built it. According to the reviewer 3, this was the first convincing demonstration of true multilingual machine translation system. However, unfortunately, as pointed out by the second reviewer, it's always a second reviewer, right? The numbers were well below the state-of-the-art existing machine translation systems. But you know, in some sense, it was the first step toward building this kind of multi-way, multilingual translation systems that scale to more than just EU Parliament proceedings. And interestingly, we could see that with a substantially fewer parameters, this system could match the performance of building all those separate single pair systems. And sometimes, especially in the low resource settings, this approach in fact worked better. And there was a great evidence that there is a natural transfer of knowledge from high resource language into low resource language. And then that's what we wanted to see, what we had to see. That was our expectation. And then this was an amazing empirical validation. This work, which was presented in 2016, early 2016, has been followed up quickly by so-called universal encoder-decoder approaches, where you have just one network that's going to work with many different languages. Our original approach had the separate encoders and decoders for separate languages, source and target languages, but it turned out that these neural nets are amazing in a sense that they can tell which language the sentence is written in automatically on its own, and then trying to extract a representation that can be shared across different languages. It has been followed up by people from the Aachen, you know, people, oh no, actually not Aachen, Karlsruhe, people from Google, and of course, you know, my own group at NYU. And then you see an example here, which was like the evidence that there was this knowledge shared using distributed representation across all these different languages. So we trained these models using only the parallel corpora that consist of sentences written in one language at a time. However, once the model is trained, we can give a sentence written in multiple languages, or the sentence with the so-called intra-sentence code switching. So in the first example, it's from the Google Neural Machine Translation. The input is written in the combination of Japanese and Korean, and the model just automatically translated into English, and this translation is perfect. Second example is from my own work done by my PhD student, Jason Lee. This model was trained to translate any one of German, Czech, Russian, and then one more Finnish into English, but it was never shown a sentence that contained more than 2 languages. But then when we gave this model a sentence written in 3 languages, that is Czech, German, and Russian, this model just beautifully translated into English without knowing which part of the sentence was written in which language. And this is really exciting, right? So this is exactly what we wanted to see, what we expected to see, and then we were able to find that evidence. Even if such a system back then was not the state-of-the-art system, we knew that this verified our conviction that such a multilingual system should work. And then because of that, people have followed up on that, ever since. And even now, people are working on it. For instance, last year, Google Translate released and then demonstrated that we can build a multilingual neural machine translation system that was trained on 25 billion training examples. And then these training examples consist of more than 100 languages. And then they were able to show that such a system can dramatically improve the performance on low resource language pairs, which is what we want, because we want our machine translation system to be able to lower the digital barriers that were set up by the skewed availability of languages on the internet. And then nowadays, production systems, so production machine translation system, not the research-oriented or the academic system, but the production systems use these multilingual systems. They have been doing that ever since 2016, 17, and 18. Facebook machine translation systems use these multilingual systems, and then they tend to really help with the low resource language pairs. But of course, the problem really has not been solved yet. So what we knew is that, okay, this multilingual translation system works really well on observed language pairs. And then, people have been pushing the boundary on those observed language pairs, but, known problems tend to be boring. We want to actually identify unknown problems and then trying to address those unknown problems. And then one thing that we didn't know back then, which was in fact mentioned in our original paper in 2016, and also was pointed out by the reviewer of that paper, is that we didn't know whether such a model would work on unobserved language pairs. For instance, if I train this multilingual system to translate from any one of English, French, Spanish to any one of those languages, and then if I use only the resources that goes through English, because that's often most of the resources that we get for building machine translation system, will this system be able to translate a Spanish sentence into French sentence without any direct resources? Weirdly so, we never asked that question in 2015. So we had to ask this question and then see if it works. And then there was a very strong suspicion that it might not work because this neural net has never seen such a pair. It turned out that that suspicion was correct, unfortunately. When we just used this system to translate from Spanish to French or French to Spanish, it just didn't work. And then that's what and then this is a setup that we refer to as zero-shot translation. So we had to come up with a elaborate scheme to build a pseudo-parallel corpus by going from Spanish to English and then back to French. So going to the English to French, and then trying to use the French to Spanish as a back translated or the cross-lingual back translation or the cyclic back translated examples. So then what we could do was that, okay, we could kind of force this model to be able to translate between language pairs that it had not seen during training. But, it felt a bit ad hoc, right? So, like whenever there is a problem identified, there are two ways to go. One way is to somehow come up with a solution, often the engineering solution, that's going to somehow make this problem disappear, even though we are not entirely sure how this solution made this problem disappear. So that's what we often do, and then that's what we have to do in order to make progress. But at the same time, we have to also figure out why the problem disappeared and whether the problem actually disappeared fundamentally. Maybe the same problem was just pushed to another side, and then the problem still exists. So what we have been doing recently, so recently as in like last year, is that trying to figure out where this issue of the zero-shot translation or the impossibility of the zero-shot translation comes from. already in Google's paper in 2019, they suspected that the model does not learn that because there is the, spurious correlation between source and target languages. Because we only have a very specific set of language pairs, what this neural net learns is not to learn to translate or choose the target language based on what we tell this neural network to do so, but instead it's going to learn that oh wait, hold on, the input is Spanish. Of course, I have to translate into English, and I should never be able to translate this into French. But that's not what we wanted to learn, right? So there's a spurious correlation that appear due to the lack of the availability of all these, beautiful paracorpora. And then in this work by Google was followed up almost immediately by me and my collaborators, especially led by Jiatel Gu at Facebook AI Research. And then here we were able to show that the mutual information between target and source languages, not the actual content of the sentences, were growing as training continued. And then as it grew, the performance or the translation quality also dropped because the model simply gave up on learning anything about translating from one language to another that was not observed before. So, it's just ongoing problem. So we have identified the problem. We have some evidence why the problem is happening. That is that the model is capturing these spurious correlations. However, that does not mean that we have figured out the solution to address this fundamental question. We do have some, let's say, some kind of ad hoc solutions, such as using a target-side language modeling to initialize a target language model, trying to use a cyclic back translation to make sure that such a spurious correlation disappears. However, we don't really have the solution that is satisfactory. So it's an ongoing work. But at the same time, we knew that there was even a more challenging problem within our site. The issue is that what if there's no parallel corpus? So let's take as an example a pair of languages, Korean and Portuguese. There's almost no corpus of Korean text directly translated into Portuguese and vice versa. You won't see them. You're going to see quite a few resources on Korean and English. You're going to see quite a bit of resources on Portuguese and English and Portuguese and Spanish, but you'll never see a resource that goes from Portuguese to Korean directly. And then if you think about how many living languages there are, according to Ethnologue, there are more than 7,000 living languages, then the number of language pairs that we can imagine is more than 25 million. Absolutely no way we'll be able to build parallel corpora to cover 25 million language pairs. And the largest, in terms of the number of language pairs, largest parallel corpora that I know, corpus that I know of is by Holger Schenk from Facebook AI Research Paris that covers only 1,620 language pairs derived from Wikipedia. And that's so far away from 25 million language pairs, right? So what it means is that often many of these data science machine learning problems can be solved and can be addressed to a very large degree by collecting more data and then you're processing data correctly. But there are these problems where it's just impossible to collect more data. How are we going to collect data to cover 25 million language pairs, right? Most of those 7,000 living languages have less than 100 speakers, so we won't be able to do that. So we had to come up with something dramatically different. And it was 2016 when Eneko Aguirre, who is a professor in the University of Basque Country in Spain, and then he was telling me, oh, suddenly the sound is lower down. Okay, can you all hear me as well? Or Rodrigo, how do I sound?
I can hear you well. Yeah.
Okay, I'll continue. I'll try to speak up a bit. Okay, and then Eneko told me about amazing research his student and he had been doing back then. Then that student was Mikel Artese, And then what he told me was that they were actually able to align two sets of word embeddings from two different languages without any dictionary entries. That is, what they did was to take the dictionary in English, for instance, and then get the word embeddings of all those words. And then they took the dictionary or the vocabulary of in Spanish, and then you get all those words, and then you get the embedding of the Spanish words. Of course, and then they don't know the correspondence between these words. But somehow, by using these continuous word representations, they were able to align them almost perfectly without any supervision. Of course, the question had to be asked, can we do that at the level of sentences or documents? If we could align automatically without any supervision by using these amazing representations or the translation systems that we have been building with the neural network, what that would imply is that we can build the translation system without any parallel corpus, so without any supervision. And that was the initial step at unsupervised machine translation. And then this was heavily inspired by the iterative procedure for aligning word embeddings. The idea was to let's extract a representation that works for both languages using denoising autoencoder, and then trying to use the idea of the cyclic back translation or just back translation in order to create all those pseudo examples in order to tune the system. And then we go back and forth between these two steps until it converges. And then it turned out that this system, in fact, creates an unsupervised machine translation system that came close to 75% of the comparable supervised system in terms of BLEU score for French to English and German to English translation, which was amazing, right? So we never knew that we could do that. And then somehow it was possible. And then this was the step toward addressing this issue of not having enough data that cannot be collected further. Of course, we were not the only ones working on it. Guillaume Lempel and others from Facebook AI Research Paris worked on it independently in parallel. And then also it was very quickly followed up by the Yang et al., and then who used the adversarial learning. And then now, since then, so that was 2018, now it's been about 2 years, the unsupervised neural machine translation or the unsupervised machine translation has become an established problem. And then Artes et al. And Lampo et al. Have been pushing the state of the art or the boundary without using any parallel corpus. And then we are almost at the level where for a particular language pair with under particular conditions, such as having a comparable monolingual corpora from a similar domain, we can build a unsupervised machine translation system that works almost as well as a supervised machine translation system. So this is amazing, amazing progress we have made over the past 6 to 7 years. Of course, this whole journey started more than 30 years ago in 1987. However, the journey has not been linear, right? It's been a very non-linear progress we've been making. So then you start wonder, why, how has it been so successful? So what is the trick these neural networks learn or they use that allow it to be a very effective machine translation system when translation is one of the most difficult problems that we know how to solve now. So one thing is that these neural nets solve a problem by utilizing or exploiting many weak rules. And then let me just quote Jeff Hinton, because I think he beautifully expressed what it means by using many weak rules. When you train a neural network, it will learn 1 billion numbers that represent the knowledge, that is the rule, it has extracted from the training data. And if you put in an image, out comes the right decision. Now, in our case, it's a translation. If there were any simple rules for deciding whether an image contains a pedestrian or not, it would have been solved problem. It would have been a solved problem ages ago. Makes sense, right? So we give a lot of data. These neural nets are going to extract all those small weak and sometimes contradictory rules. That's why we need all those parameters and all those neurons and the many layers. And then it's going to use the combination of all those rules in order to generate the decision. And in our case, decision was a translation. And furthermore, we have to think about how those rules actually arise. And then it turned out that it's really important to have a large amount of data, regardless of whether we have fine-grained annotation or not. And large data is necessary because this neural net needs to look at enough weak rules in order to solve the problem. Furthermore, in order to store all these many weak rules, we have to have a large models. And then we have to use a deep neural networks because all these rules must be arranged in a hierarchy to be both efficient and effective. But then, of course, a lot of the skeptical kind of responses I receive when I talk about this is that we knew that already in 70s, 60s, even in 50s when Rosenblatt proposed the perceptron. So what changed, right? Has anything changed? Is it possible that it's just the NVIDIA that has changed the whole field by creating all those GPUs, and then it's Google that has learned to create all those gigantic data centers and release the Hadoop and so on? Turned out that that's actually not true. So the high-level abstract ideas are indeed from 80s and 90s. However, over the past 30 years, we have made advances that without which we couldn't have made these amazing systems. So let me just take as example a few aspects of them. One of them is a better parameterization or / architecture. We now know that we want to use non-saturating activation functions in order to facilitate learning. We now know, based on the LSTM and GRUs and ResNet, as well as the attention, that we want to ensure that the path or the computational path between the input and output is as short as possible, but then it has to be adaptive and dynamic. We know that the normalizations are important. And furthermore, we have so much better understanding of learning and optimization. We know that using SGD is important. We know that the proximal regularization, that is ensuring that the models learn at a very constant rate, is important. Furthermore, we now know and have a way to integrate multiple sources of signals. We know the importance of the multilingual as well as multimodal learning, and also we know the importance of the multitask learning. And then unlike in 1997, we know how to use them better. So all these, let's say, advances that we have made over the past 30 years have made it possible for us to build this kind of amazing neural network for the natural language processing and machine translation. Now, that doesn't mean that the problems have been perfectly solved. I don't know if you have tried Google Translate. Google Translate is one of the best working commercial for free service translation services you can use, but you notice that it's far from being perfect, right? For very small number of languages, it works almost perfectly, but for majority of languages, that's not true. There are a lot of things that we need to fix. So my research continues. At the end of the day, what we do with this language generation system is to do the probabilistic sequence modeling. That is, let's trying to build a neural network that's going to assign a probability to a target sequence given some input context, which I denoted as C here. And then this probability model has to be estimated or inferred from a finite set of data points. There are often three ways to go whenever you build this kind of probabilistic model. One is to build a gigantic table. You're going to build a table where first column contains all possible context or the input, second column contains all possible outputs, and then the third column is going to have all those probability values. Not a good idea when you're working in this kind of structured combinatorial space where the size of the space grows exponentially with respect to the length. So that's not that great. So then what we need to do, and then what machine learning tells us to do, is to either to factorize a table that is trying to model all those conditional distributions instead of the joint distribution, or to smooth the table. That is, introduce a hidden variables, and that hidden variable is going to have a lower dimensional structure that's going to capture the probabilities. But then, of course, inevitably, because it's a lower dimensional latent variable, probabilities are going to be smoother than usual. So let's look at the autoregressive model. I know that I'm running out of time a bit, so let's talk about BERT quickly. There are three ways to talk about BERT. I'm sure every one of you now knows about BERT, and then you may be already using it in the course. You probably have learned about it. But then BERT can be thought of as studied from three angles. One is that to study it as how well it works for transfer learning. Second is to understand what BERT learns. And then third is what BERT was actually trained to do. I'm going to focus on the third part, but let's talk about, and because the first part is not really interesting anymore, right? We know that it's amazing. You look at the super glue, all those, let's say, benchmark natural language understanding or the classification problems. Every single top rankers use a pre-trained language model that was inspired by BERT and Elmo. Okay, so good. These models actually do initialize classifiers really, really well. But then, of course, the second aspect is that how is it doing so? What are the things that this BERT or the pre-trained language models are capturing that allows it to be a good initializations for downstream classifiers? There are many different work that tries to analyze it. Some of them are more interesting than others, but in general, what we see is that these models do capture the linguistic properties that without us having to explicitly encode it into it. By looking at all those data points, it just captures all those weak rules that I was talking about, and then those weak rules turned out to be linguistically plausible. Not that everything is like that, but mostly so. However, one thing I want to emphasize is that this kind of analysis or the effort to interpret what is going on inside the neural net is very, very dangerous. Let me just quote what E.Y. Tae, who is a professor in Oxford and is also at DeepMind, said in his NeurIPS 2017 embodied talk. The parameters of the neural networks, consequently the internal activation of the neural networks, don't really have meaning because these neural nets are not identifiable. That is, when we start from a neural network, and then let's say we generate the data from this ground truth neural network. And unfortunate thing is that if we train another neural network on this data that was generated from the original neural network, we won't be able to, in fact, find the original neural network because of the permutation issues and whatnot. Instead, we should think about the space of functions. That is, what is being computed? Then can we find the neural net that is going to compute the same thing as the original neural network? What it's saying is that we have to be careful. Otherwise, we may be reading 1 million or 1 billion tea leaves. That is, this gigantic BERT. And then when you have millions or billions of the tea leaves, you can see whatever you want. So one example I took it from Wikipedia. On the right panel of this slide is an example of tea leaf reading. And then according to the reading of this tea leaf, there are a dog and a bird. Do you see dog and a bird? I don't see neither of them, right? But some people apparently see it because they want to see this. So we have to be careful, and then we can do that with the neural net interpretability as well. It's a very difficult topic. So instead, we're going to talk about what BERT was trained to do. So BERT was trained with an objective function that is often referred to now as the masked language model. The idea is that there is some ground truth distribution, and then we want to train this BERT, but then this BERT is going to be trained to match all possible conditional distributions induced from this ground truth distribution. And then we're trying to minimize the divergence between what BERT predicts this conditional distribution to be and the true conditional distribution is. And then how we generate all these conditional distributions is by randomly masking some of the words in an observed sequence, or that there is a sentence. And what it means is that because BERT learns a distribution, we can in fact generate a sentence or the document from BERT as well. All we need to do is figure out what is the right set of conditional probability distributions that we use in order to define a proper joint distribution from which we sample. And this optimal dependency structure turned out to be conditioned on the input C. And then this was pointed out recently by David McAllister in his blog post, which is highly recommended. So what it means is that we can now come up with a sequence generation algorithm for BERT that is quite interesting compared to the existing autoregressive model, in that we not only need to decide which word needs to be generated next, but we need to decide which location that word is going to be inserted as well. So we're going to alternate between determining the next set of variables to replace and then sample the value for the variable using BERT, and then determining which next word variable we're going to replace, and then go on until we figure out the values of all the variables in the sequence. So suddenly, this generation is not monotonic left to right or the right to left. It's in fact adaptive order generation. And of course, what we want is not only this kind of high level abstract notion, but an actual mathematical and quantitative description of what happens. And then this can be written down as the probabilistic model of both ordering and generation. So we wrote this paper last year. This paper has been rejected over and over, but this whole idea actually still stands. And then once we have this probabilistic model, then we can actually generate from it by trying to maximize the probability or the log probability assigned by this joint model with respect to not only the actual words, but also the ordering in which these words are generated. Of course, we need to now decide on the parameterization. For the sake of time, I'm going to skip this, but if you have any questions, you can email me, or you can actually take a look at this paper by Elma Mansdorf and Alex Wang. It's a pretty well-written paper. And then what we saw was that the BERT is indeed able to generate a sequence in an order that is quite non-trivial. It turned out that the optimal order determined by BERT is not necessarily monotonic going from left to right or the right to left, but it's going to depend on what kind of strategy it thinks is most optimal. So for instance, this is one particular example I found. And then the source sentence is written in German. I have absolutely no idea what it means in German. However, the reference translation that was extracted from the data said that yet without civil society organizations, a democracy cannot function. Now, starting from the source sentence, this BERT-based model is going to determine what the length of the translation should be. So it's going to be all empty sequence. And then it determined that, okay, it needs to put the period at the end first. And then the democracy cannot, and then jumps back to the beginning of the sequence, put the without, but, and the society, and then comes to the middle to put the semicolon there, and then trying to fill up the rest of them. So it was actually it already knew how to write it, not only in terms of which words to put one after the other, but also where to put them. So not quite state of the art, but we're getting there in terms of this learned order generation. But the interesting implication from this kind of learned order generation or learning all those conditionals simultaneously is that we can now imagine so-called constant time machine translation. Assuming that we have a good enough parallel compute resource that is like using GPUs, what it means is that we can generate multiple words simultaneously. And then by learning which chunk of the sentences the sentence needs to be generated in order in parallel, we can now determine, we can now impose a constraint on how many steps the machine translation system can take in order to create a translation. Now, this is very different from the existing conventional approach, right? Why is it different? Because conventional approach that is going from left to right monotonically implies that the translation is inherently linear in computation because we have to generate one at a time. But it turned out that's not necessarily true. We can now build a system that is flexible in the way in which the sentence is generated, and then that allows us to do so-called constant time machine translation. Now, it turned out that obviously I was not the only one to think about this idea. Birth generation was pursued by two additional groups independently, one from Facebook AI Research Seattle by Marjan, and then the other from, I forgot actually where they are, I think they are in Germany, Lawrence et al. And last year all together. And then there are different ways to do such a learned order generation, not necessarily using this BERT, but also training the whole thing end to end using imitation learning. The first of the kinds was pursued by the Sean Welleck, who is my PhD student last year. And then there's been a series of papers along this line of trying to generate things not in a given order, but in a learned order. So let's see, it's already 6 p.m. So I have this probability sequence modeling part, but I guess I'm going to skip this. It's a very interesting thing, but you'll be able to read about this from my Google Scholar page because I've been working on this a bit further these days. Okay, but then I wanted to talk about a bit of a looking forward for the, let's say, another 2 or 3 minutes, if it's okay with you all. So it took about 30 years for us to figure out that neural autoregressive model, that is the model that you probably have learned, and then there is a model that it powers Google Translate and all the other commercial machine translation engines. So it took us 30 years to realize that that is a good way to go. But then it looks like the alternatives, such as the non-monotonic modeling and also latent variable models, are catching up quickly. It's very, very exciting. But coming up with these different modeling choices is not necessarily the only part of machine learning. Machine learning covers, and then data science covers the entire pipeline. And then when you look at the entire pipeline of how to solve the problem, you start looking at different corner cases in the problem that cannot just be resolved easily by building a better neural net or the better learning algorithm. There are cases where we have to just rethink or realign how we think in order to solve the problem better. I'm going to just list up 2 mysteries that I have absolutely no idea how to solve, but I think we have to solve. One is the phenomena called, or the coined by Hosman et al. As the neural text degeneration. We build these amazing models, and then the funny thing is that we actually don't know how to find the most likely sequence from these amazing models. These amazing models allow us to train it really well, but that doesn't imply that we can actually generate from these models well, because these models are too powerful. It doesn't have any useful structures such as linearities or the Markovian properties that are embedded that we can exploit to solve the problem of generational inference well. So, and then that actually leads to weird phenomena, both theoretical and empirical, called inconsistency. So these neural autoregressive models sometimes do not work well with these decoding algorithms that we use, such as beam search and greedy decoding. And these neural autoregressive models tends to put gigantic amount of probability mass on the origin, that is the zero length sequence. What is the right way to solve this? Do we have to go back to the structured perception and all those structured prediction algorithm to train these models better? Maybe we can just avoid this issue by coming up with a good inference algorithm. The biggest issue here is that we actually don't know what are causing this issue. We know these are the problems, but we don't know what are the causes behind this issue. And that's what makes it really exciting, both exciting and also very challenging. And then second mystery, oh, actually, I'm sorry, I was going to talk about the 3 mysteries. So second mystery is that what is being captured by these neural networks? And then are we actually looking at the correct thing? So everyone wants to interpret or explain what these neural nets do, and I'm one of them as well. And then there are some indications and then some of the attempts that when we use, when these models, or when we see that these models capture these linguistic structures, these models tend to solve the problem better. And then because of that, a lot of people, including myself, have been trying to encode the linguistic structure explicitly into these neural networks. But then I realized at some point that maybe we never actually asked the right question. Maybe we just wanted to see that these models are capturing something linguistic. Perhaps what we should have asked was that are these linguistic features that we think are useful really needed by these neural networks to solve the problem? There is a very interesting paper by Famel that was published in a very interesting and strange journal. But this paper has an amazing insight or amazing observation there is that they saw that the neural machine translation system they trained were able to extract dependency parse very well. And they conjectured that these dependency parses are needed by this neural net to solve the problem of translation better, which is what everyone would kind of guess, right? But then what they realized is that they could actually explicitly impose the attention pattern to be linear rather than follow the dependency parse. And then they saw that this model actually worked better. So when this model was encouraged not to capture those linguistic information, in fact, it was able to solve this problem even better. Then what were we seeing when we saw that these transformers were able to extract the dependency parses? Furthermore, Kovaleva et al. Last year in 2019 also reported that these relationships or the semantic information are ever improve the performance of BERT. So they knew that certain problems that BERT can solve well needed this information of this frame semantics, but it turned out that the encouraging BERT to capture such frame semantics did not help it at all. So then, is it possible that we've been chasing ghosts by trying to find something linguistic from these models? That's a big mystery. So the final mystery that I want to put in front, which is not like the only mystery that I find, but a mystery and the challenging problem that a lot of people are finding these days is more on the side of the causality. So let's just imagine a scenario where I have a corpus, and then in this corpus for machine translation, every single banana or the occurrence of banana is preceded by yellow, because maybe the person who wrote this text never saw green bananas. In fact, I only saw the green bananas only like 2 years ago when I was in Kigali, Rwanda. There's a picture in the slide. And let's say that is the case, and then we train this machine translation system on this particular corpus where bananas are always yellow and never green. Now, how would the model figure out whether it needs to look at yellow in the source sentence in order to put yellow in the target sentence? So noran banana written there is Korean, rather than trying to put yellow in the target sentence by looking at banana, because every time I see a banana, it's yellow, right? So how can this neural machine translation system avoid this issue? Maybe giving more information, such as giving information of the visual vision could help, because the neural machine translation system might figure out that the yellow is a color of an object, and thereby the object itself should not induce the yellowness. Maybe the model can actually figure that out automatically. Maybe we need to give the model an ability to experiment in the word. Maybe we should send the model into the word and then ask it to find a banana that is not yellow. If it succeeds in doing so, we'll learn that the bananas do not have to be yellow. But it's up in the air. Nobody knows what is the right way to answer this question. So this is the final slide of mine. And I'll hang around, I don't know, like the 10, 15, 20 minutes to answer your questions. But I wanted to just say that we have made a great progress, but in the grander scheme of trying to build a machine that is intelligent, the amount of progress that we have made is so tiny or minuscule that there's, there's no reason for us to even think that we made any progress. So in other words, so exciting, and then there are so many things that we can try, think of, and then try to solve. And that's it. Thank you very much for listening to this long talk.
Oh, thank you, Professor Cho. I'd like to ask the audience just to unmute your microphone, just to give him a sort of applause. Yes.
I guess we have to unmute everybody, like they cannot.
All right. You can mute, yes?
No, I think the participants, the attendees actually click the, clap
right.
button or something like that, right?
Okay. Anyway, thank you for this inspiring talk.
Thank you.
Rodrigo, do you want to manage the questions?
Yeah, you guys can ask questions in the QA section here, dialogue, and yeah, or you can just unmute and then we can read.
So I actually like they organized the iClear earlier, so I know how to use webinar quite a bit. So what you can do is that you can click the hands up button. In the attendees can click the hands up button, and then Rodrigo can see the the person with the hand up in the participant list, and then Rodrigo can allow them to talk. Right?
All right. So there are a ton.
Or anyone can make a question there.
Oh, there is a question. Okay. Let me try to actually answer this question by Gabriela Sorita. So what do you think about the transformer architecture? Do you think it's something revolutionary, or is just some local minima that has been successful in the last couple of years? Is there anything fundamentally different there? This is an awesome question, right? So most of the results that I've shown you, except for the historical part, do use transformer architecture. Transformer is an amazing architecture in a sense that it avoids the issue of the recurrent neural net, which is that the recurrent neural net needs to compress the history. So this compression is always problematic because the compression is a very nonlinear process. And then once, even if you compress it, decompression also requires a heavily nonlinear processing that may be difficult to learn from data or with a finite amount of parameters. But the transformer avoids that by exclusively relying on the attention mechanism. So in a sense, when we have a reasonable length input, and then you know that long-range dependencies are important, it's definitely the way to go to use transformers. However, that comes with the the significantly increased computational complexity because you have to compare the query vector against all the key vectors and then trying to compute the weighted sum every time, right? So that's not going to scale up if you start thinking about, okay, what if I want to use transformer to solve a problem such as in the continuous control or the lifelong learning, where the number of the steps is going to be in the order of millions or billions. I cannot compare the, apply the attention over millions. What it means is that there is a natural problems where the compression is necessary. And then it looks like the recurrent net is a good way to compress the past according to what kind of problem needs to be solved. Now, there is a problem that recurrent neural net cannot avoid, is that we need to use a backpropagation through time. But it turned out that the backpropagation through time is not the only way to train recurrent neural network. We can rely on a concept called real-time recurrent learning that allows us to update the recurrent neural net on the fly as we go forward. And then, recently there has been a number of papers that propose a variance of the real-time recurrent learning that is scalable and then usable. So I think in the future, it's more going to be like, what is the problem that you want to solve? What are the properties of the problem? And then what is the right way to combine these different architectures to parameterize your policy or the distribution that you're learning? And then trying to figure out what is the right learning algorithm to learn train all of them. So the answer is that the transformers are awesome, but then it's not going to be whether it's transformer or not, but rather where can this transformer be used best, and then what other things we need in order to solve a challenging future problems.
Right.
Okay. And I think my talks often are very clear so that the people don't have too much questions. Yes.
Yes. Did anyone raise their hand? Oh yeah, there's one here. Paula Costa.
Mm-hmm.
Yeah, you can unmute. All right.
Okay. So first of all, I would like to thank you your lecture. It is really inspiring because you showed all the people that worked with you, and you also inspired us when you say about the journey and eventually not focusing only on the state of the art.
Yes.
And regarding text to sign language translation. Did you explore that? And what do you think that would be the techniques that we could use to do that?
Right. So I haven't actually looked into the text to sign or the other way translation, just because like the limited time. But there are quite a few groups in the world who are working on the kind of automatic generation of sign and also the sign to text generation, because that's going to be amazingly useful for like the deaf people to be able to talk with the others like without any issue, right? So now. The challenge there is that the amount of data is actually pretty small, and then is the domain where the data is available is very limited. So it's often the political speech, parliament's proceedings, and the news where you have enough data. And then like the broadcasters are never good at sharing their data. So but then you rarely get a, let's say, sign language paired with the actual text from the, let's say, everyday conversation. So that's going to be one particular, let's say, challenge that needs to be tackled in order to build a usable and then the broadly applicable sign language translation system. But I think it's doable. So there has to be a will, and then there has to be a group dedicated to that. Because my lack of experience with the computer vision, I'm probably not the best person to work on it. But I do know that there are a number of groups that are working on it, and it's an absolutely worthwhile problem to tackle. Yes. I hope that answers your question.
Yeah, for sure. And just regarding your last slide, do you think about training machine translation with multimodality? I mean, with image and text?
Yes, so the multimodal machine translation is in fact a subfield of machine translation that started about 2018-17. So there are certain sentences that do benefit from having access to images, but the thing is that most of the sentences do not benefit from having images, which means that it's not that we don't know how to build such systems. We're actively trying to build such system, but evaluation has to be much more fine-grained than usual evaluation of machine translation systems. Because if you think about it, most of the sentences, you can translate them perfectly without knowing the scene in which the sentence was written or spoken, right? So what is the right way to evaluate it? That's one thing that I didn't really touch upon in this talk, but that's the one important direction in multimodal machine translation. So yeah, you can look, search for multimodal machine translation, you'll find a lot of resources there. So I think we can go to the QA question in the QA panel, actually. So there's a question from David Castro Reyes. Written text is the only, yeah, this is the question about multimodal translation, right? So essentially what you want is that you want to build a system that is able to take as the input as much context as possible that goes beyond the text. So yeah, should check out the multimodal translation. So the next question is from Diego Andres Mendez. So question is, are there any requirements for the training data? Data on rare languages is probably very noisy. So this is a big problem. Noisy data does indeed lead to a worse system that exhibits very weird behaviors. So one thing that a lot of people in production, a lot of people who are developing production systems do is to clean up their training data, because it turned out that these neural nets are so amazingly large and capable of capturing all those small rows. Whenever there is a noise, it can also capture those noise as well. So what is the right way to denoise the training data is itself a research topic. And then you should go to the WMT homepage, and then they do have a new track on how to prepare the paracorpus or clean up the paracorpus. Many techniques using denoising autoencoders, back translation, and others are being investigated. So the next question by Roberto Jr. is, do you think there is a kind of Esperanto, language for machine translation? It'd be an optimal bridge language. Oh, okay, this is an interesting question. So one thing we have so far learned is that when we build this kind of machine translation system, and then I'm going to talk about particularly about the neural machine translation system with a single language pair, assuming that the amount of data and the quality as well as the diversity of the data is controlled to be same, then we do not see the difference between different languages. So for instance, a lot of people think that of course, English to French translation is inherently easier than, for instance, English to Korean translation. However, when the amount of resources and quality of the resources is well controlled, we actually do not see such differences across all those different languages. In fact, most of the languages seem to be more or less similar distance from each other in terms of building these machine translation systems. What that probably implies is that it's not going to be a human or natural language, although Esperanto is not really natural, but it's not going to be a human language that's going to serve as an optimal bridge language. Rather, it is this continuous internal representation of a neural machine translation system that works as a bridge between all these different languages. Perhaps that continuous representation could be thought of as an intermediate language. Okay, I mean, I think it's already 6:20, and let's see if there are more questions.
All right. Yeah, please raise your hand if you.
Maybe just for last question.
Yeah, either raise your hand or ask in the QA section.
Okay, so there's the last question. Yes, by the Edgerson Casanova. The question is, do I think voice cloning, multi-speaker voice synthesis can be successfully employed in automatic machine translation audio to audio? Yes. Okay, I see. Could this be a viable way for resourceful languages? Yes, this is a really great question. At the end of the day, most of the commercial machine translation systems are text-to-text. And of course, people do build the speech-to-speech translation by simply training speech recognition system, machine translation system, and then the speech synthesis system. But obviously that's not ideal because there will be the error that is going to be accumulated and propagated. So one of the biggest challenges in building speech-to-speech translation system is that the large amount, if not the majority of resources that we have in order to train these machine translation systems are written, and then they are well-formed. On the other hand, speech is never well-formed. If you think about it, and then if you listen to yourself whenever you have a chit-chat with your friends or your family, you notice that the number of sentences that are well-formed when you just talk casually is extremely low, because we go from one to another topic within a sentence. We lose the track of how we started a sentence and start talking about something else. And then those are all ill-posed sentences. And then our machine translation system tend to be poor at translating such text because those were not the text that the systems were trained. So the big challenge in building this kind of speech-to-speech translation system is how to build a speech recognition system so that it's going to create a transcript that's going to be easily translatable by the machine translation system. And then machine translation system is going to create a translation that's going to be natural, not when it's written, but when it's spoken. And furthermore, we're talking mainly about the content when we think about the machine translation. However, when it comes to speech-to-speech translation, it's not only the content, but also the style. So what is the right way to carry over the style from speech of the source into the target while keeping the content translated correctly? So it's a really, it is a viable problem. A lot of companies are working on it, but it's just turned out to be very difficult. So I think there is one last question on the chat window. I think that, okay, that's going to be the last question. Let's do it like that. Right. All right. And then if you have any questions, you can always ask Rodrigo, you know, he'll be able to answer as well as I can. So that's fine. So the last question by Daniel Hoyos is, can we use DL-based NLP techniques to aid in the creation of computational linguistics tools for poorly studied languages? For instance, indigenous languages. Yes, perfectly. So I often get asked, you know, by the linguists and computational linguists whether their existing tools or the frameworks or the paradigms could be useful for deep learning, for natural language processing. And my answer is always that it should be the other way around. How much text can a single human linguist read in their entire career? And in fact, let's not go for a single linguist, but the entire linguist in this human history. What is the amount of text that they can read and digest and then come up with a theory? That's going to be much smaller than the amount of data we can make or let our neural network consume within a week or so. What that actually implies is that these neural nets are extracting all those interesting linguistic phenomena, not only from a single language, but from all the languages that we have resources about. And then as I have shown you earlier, these multilingual systems know how to transfer knowledge from one language to another. And then in particular, we observe that the low resource languages do benefit from having high resource language together. So yes, the answer is yes. And then I do believe that the one possible and a very promising future of computational linguistics is to figure out what these deep neural nets are figuring out by looking at amazing amount of data that is not going to be of single language, but of the multiple languages, and then trying to see for those poorly studied and low resource languages, what this network learns. So answer is yes. So I guess, you know, I can wrap it up. Vikram, you should check out the programming language translation. Just Google search it, you'll see a lot of them. It's still ongoing work, but I think that there is a very interesting things coming out of the Guillaume Lempo at Facebook AI Research. All right, so thanks for the invitation and thanks for listening to me all the way. And again, thanks to, you know, Roberto and Rodrigo for arranging this. And sorry, I had to, you know, I couldn't make only this evening slot and couldn't make it in the early morning. Sorry about that.
Okay, thank you very much, Professor Cho, again. It was a pleasure to have with us this evening. Thank you.
Yes, thank you.
Yeah, thank you very much. Yeah.
Rodrigo, I'll talk to you later. Yes.
All right, thank you. Bye-bye.
Okay, thank you.